why they matter for us today. Amy, if you want to share your screen.
Sure, I'll just share my screen. There's a few steps for me to get my presenter notes. Rehearse slideshow, new share, advanced portion. All right. Can you all see just my screen? Let me just
looks great, yeah.
Slightly. Oh, no, I think that's okay. Cool. So thank you. And hi, everyone. I'm coming to you from Melbourne, Australia, in the evening, on Sunday evening. Thank you for all being here on your Sunday mornings for most of you. And I'm coming to you from Melbourne from the unceded lands of the Wurundjeri Woiwurrung people. So I'd like to pay my respects to their elders, past and present, and also extend that respect to all Indigenous peoples on whose lands that we've worked for studies presented in this talk. And I'd also like to thank the organisers for inviting me to be part of this conference. It's been a really fun conference so far, and I really like the innovative format. It's a great format for an online conference, and hopefully it will lead to us making more of a difference with our data. So I'm happy to be part of that. So in the presentation today, I want to talk to you about sclerochronology. And for those of you unfamiliar with that term, I'll define it in just a minute. But I want to talk to you about some of the ways that applying sclerochronology from mollusk shells from archaeological sites can help us deal with modern day climate change and sustainability. So what is sclerochronology? Sclerochronology is the study of physical and chemical variations in the accretionary hard tissues of organisms. The most common organisms used for sclerochronology are corals, mollusks, otoliths, and teeth. And sclerochronology is based on the fact that these organisms deposit their hard tissues incrementally. So much like rings on a tree in dendrochronology, but instead of looking at wood, we're primarily looking at carbonate. And so the growth and chemistry of this carbonate is modulated by the environment. And so therefore analysing this growth and chemistry can provide high resolution snapshots of environmental change ranging from annual to sub-daily resolution. Sclerochronology is an incredibly useful tool in zooarchaeology. There are many organisms with incremental hard parts that can be preserved in archaeological sites. So, and often they're the remains of ancient meals, things like bivalve and gastropod shells, otoliths from fish, and teeth from various animals. These archives and their associated proxies can provide environmental information across marine, freshwater, and terrestrial realms. And they can provide high resolution environmental information that can be directly linked to records of human behaviour, not only because they're found within archaeological sites, but because they're the remains of ancient meals, so their death is the result of human collection. We can also use the growth patterns and geochemistry of the last deposited growth increment in archives such as bivalves, gastropods, and teeth to reconstruct season of death information, so therefore allowing reconstruction of hunting and foraging patterns. We can also look at geochemical patterns of oxygen, carbon, and strontium isotopes in animal and human teeth to reconstruct migration patterns, and also pastoralism practices such as transhumance. And there's many other novel applications, including things like assessing taphonomy and yielding information on burning and cooking practices that we can get from sclerochronology. Another useful aspect is that biogenic carbonates can be absolutely dated using methods such as radiocarbon, U-series, or amino acid racemization to provide a direct temporal link between the environmental record and human occupation. So let's cut to the chase and to the theme of the conference. How can the application of sclerochronology within zooarchaeology save the world? It's a big claim, but I'd kind of like to look at how the kinds of data we generate can be applied to solving real world modern day problems. And really, I think this gets to one of the fundamental issues that many archaeologists face. Like, how can we make studying the past not just relevant, but useful and impactful for managing our modern world? So today I'm going to take you through two ways in which I think that we can. And so for those inclined to nod off, here are my take-home points up front. So firstly, sclerochronology can be useful for understanding adaptations to rapid climate change. Using sclerochronological records from archaeological sites provides a direct link between climate and human behaviour. And understanding how past people dealt with climate changes can inform our current adaptation strategies. Related to this, the nature of the quantitative and high resolution climate records we can generate makes them useful as inputs to climate models, which in turn aids our understanding of Earth's climate system. And secondly, sclerochronology can be used to understand sustainable harvesting practices by reconstructing seasonal foraging patterns. This becomes even more impactful if you're lucky enough to work in regions with continuing Indigenous connections to country, as combining traditional ecological knowledges with our quantitative data can lead to a more holistic appreciation of resource use, which can in turn feed into ecosystem management plans where Indigenous knowledges are foregrounded. So, onto how sclerochronology and zooarchaeology can be used to study human responses to past climate changes. So, historical and instrumental records of climate change really only extend back a few decades in most parts of the world, whereas natural cycles of climate variability are longer than these historical and instrumental records. Therefore, we have to turn to paleoclimate records where we use climate proxies to extend our understanding of past climate variability from decades to potentially up to millions of years. So paleoclimate proxies provide a way to place human-induced climate changes that the planet's currently experiencing within the context of natural climate variability. And by studying paleoclimate proxies, it's become very obvious that many of the changes we're seeing today are well beyond the range of natural climate variability. So in my own research, I'm particularly interested in the intersection between paleoclimate reconstruction and archaeology to understand human-environment interaction. So we know that climate and environmental changes affect the distribution of food, water, and the availability of shelter across the landscape, which has knock-on effects to any species relying on these resources. Rising and falling sea levels as a result of environmental changes will ultimately expose and cover tracts of land and their associated resources. And climate and environmental changes also impact the physiological tolerances of plants and animals that we rely on for subsistence. But we're not environmental determinists. Humans are not simple creatures at the whim of Mother Nature. We have complex adaptive responses. These can include things such as migration and dispersal across the planet to find the resources we need to live, changes in technology to deal with changes in the environment, shifts in subsistence, and other more culturally modulated behavioural changes that may not immediately seem intrinsically linked to environmental changes. And there have been many studies that have looked at human responses to climate changes in the past, with responses ranging from societal collapse to increased social complexity and many things in between. But many of these studies, they use climate records that are distant from the archaeological site from which past behaviours are interpreted. And these records may be decadal to millennial scale in resolution. And these records don't necessarily reflect the changes that happen close to the archaeological site. Humans respond to the climate around them at the local and also at the seasonal scale. So to understand the effect of climate change on human populations, we need local and seasonal climate records. The best place to get these is from or very close to archaeological sites. And in my research, I reconstruct climate variability primarily from using the chemistry of archaeological mollusk shells. So there are two main types of information that we can gain from analysing this growth in chemistry of sclerochronological archives. The first is getting high resolution records of climate and environment. So for fast growing archives such as intertidal mollusks or the teeth of certain animals, it's easy to get monthly or greater resolution by sampling with techniques such as milling for stable isotope analysis or using laser ablation ICP-MS to analyse for trace elements. And so we get high resolution snapshots over the lifespan of the individual or part of the lifespan of individual animals that can tell us about subseasonal climate variability. Some organisms, particularly some mollusk species, can live for decades or even centuries, depositing annual growth increments. If the growth period of several individuals overlap, they can be cross-dated, as is done in dendrochronology, to provide even longer continuous high-resolution records. So such high-resolution data are lacking in many parts of the world, and yet they're important for understanding the effects, particularly of changing seasonality on mean climate and the variability of climate drivers, such as, for example, the North Atlantic Oscillation or ENSO. And when the shells come from archaeological sites, these data are useful for understanding human-environment interaction at higher resolution scales. And so in this talk, the examples I'm going to focus on next are using marine mollusk geochemistry, looking at oxygen isotope ratios to reconstruct sea surface temperature. So the ratios of oxygen 18 to 16 in the shell carbonate is primarily controlled by temperature. And so therefore sampling the mollusk at high resolution can generate records from seasonal to tidal resolution, depending on the growth rate and the sampling resolution. So this example I'm sharing with you today is part of my ARC DECRA fellowship, and it's linking paleoclimate records from archaeological sites to understand why at around 40,000 years ago, a time of rapid climate changes, that modern humans expanded across the world whilst Neanderthals became extinct, despite many similarities in the two species. So for those unfamiliar with Neanderthals, a few things we know about them. They lived in Eurasia between about 400,000 and 40,000 years ago. They were stronger, shorter and stockier than us, possibly some adaptations to cooler climates. And indeed, they survived through several glaciations, but became extinct around 40,000 years ago. Yet they share many similarities with modern humans. We both have big brains, the ability for language. We both display some kind of culture in terms of symbolic expression, wearing clothes, making art, possibly burying our dead. Indeed, we're so similar to one another, but we even interbred, and the majority of modern humans alive today carry some Neanderthal DNA in their genome as a result of these interbreeding events. So why did modern humans survive and Neanderthals disappear? There's many competing theories, but the one I'm interested in exploring today is climate change. So a key region where modern humans and Neanderthals interacted was the Levant in the far eastern Mediterranean. And this was a particularly interesting place over the last 100,000 years or so. Neanderthals made their way here from Europe. Modern humans made their way through here on their way to Europe, probably. And it's here that they met and at least a few times interbred. Neanderthals became locally extinct in the Levant before their final extinction in Europe. So during this time, the climate was experiencing a series of rapid shifts known as Dansgaard-Oeschger events. So seen here in the Greenland ice core record as rapid shifts between cooler and warmer temperatures. And these shifts occurred within decades, so within the lifetimes of individuals. And this meant that the people living at this time, be they Neanderthal or modern human, would have had to have adapted to these rapid changes. These shifts might have caused changes also in seasonality, and this is what I'm interested in. If they did, they could have drastically changed the resources available to people at this time, another thing for them to adapt to. So were modern humans better adapted to dealing with these climate shifts than Neanderthals? So to test this, we need detailed understanding of these rapid climate events directly linked to archaeological records. So now I'll take you to one of the sites where I'm generating such records from mollusk shells, the site of Ksarakil in Lebanon. So at Ksarakil, I've reconstructed subseasonal sea surface temperature records from limpet and top shell mollusk shells from around about 45 to 30,000 years ago. So covering the time when modern humans and Neanderthals coexisted in the Levant and beyond. So here's a summary of our results from the site. So this box plot summarizes several shells per layer, moving from the youngest on the left-hand side to the oldest on the right-hand side. And you can see that we have occupation both in cooler in blue and warmer in red climatic phases. So if we take a closer look at the seasonality data now, so each of these graphs represents a high resolution sequence from an individual shell over several years of growth. In the layers dated to the cooler periods, known as Heinrich events and stadials, we get generally cooler mean sea surface temperatures and a higher seasonal range. Whereas during warmer interstadial phases, we see warmer mean sea surface temperatures and a generally reduced seasonal range. And this pattern is repeated throughout the sequence. So what does this mean in terms of human environment interaction in the region? What this pattern tells us is that the environments in which modern humans and Neanderthals were living were subject not only to varied temperature, but also varied seasonal regimes. And this fluctuating seasonality would have led to unpredictable swings in resource timing and availability in the landscape. So why did we survive these changes when Neanderthals didn't? From our perspective as Homo sapiens, it's tempting to see our survival as inevitable due to our superior physical abilities or intellects or culture. However, if we go back tens or even hundreds of thousands of years, this doesn't seem to be obviously the case. So this is a really nuanced debate, but from my perspective, we can begin to distill it down by linking our environmental data more closely with archaeological records from the region. So modern humans seem somehow resilient to these rapid climate shifts. Was this due to subtle differences in their behaviours or culture? We know that they had broad subsistence strategies, eating a varied diet of small and large animals, shellfish, plants, and they had diverse toolkits of stone and bone. They also lived in larger and more connected groups from both archaeological and genetic evidence, and seem to have broad exchange networks, evidenced, for example, by the occurrence of similar technologies at widely dispersed modern human sites. Neanderthals, on the other hand, seem to have slightly less varied diets, focusing on larger game species, although this was not always the case, and diets were also regionally varied. Their tool assemblages were not as diverse, and they tended to live in smaller groups. Neanderthal population density was also already low around 40,000 years ago, possibly due to a combination of factors, including environmental change, natural disaster, and disease. And this probably allowed Neanderthals to eventually be genetically swamped and assimilated by modern human immigrants who are more adaptable and resilient to climate change. So humans have dealt with rapid climate changes throughout history and prehistory, and this is just one example. Can we learn anything from this episode that happened tens of thousands of years ago that's relevant to our modern world? I mean, I think so. So from this and other examples, we know that species that did not adapt faced extinction. Societies that did not adapt faced huge changes or sometimes collapse. So being flexible, resilient, and ready to adapt to changes is a key lesson, I think, that we can take from archaeology into our modern world. Some keys to adaptability we can surmise from looking at archaeological records include broad societal connections, broad resource bases, not over-reliance on a few key resources, and having friendly neighbours and trade. And so in this last part of the talk, I just want to briefly touch on how we might use archaeological sclerochronology to understand sustainable harvesting practices. So really key line of evidence that we can also get from analysing oxygen isotope ratios from mollusk shells is information on seasonal foraging patterns. So the pattern of variation of the final growth portion reflects the climatic condition at the time the animal died, and this can be used to reconstruct the season in which the animals were collected by humans, and therefore also when the site was occupied by people. Other archaeological seasonality methods, such as the presence of migratory or seasonally available plants and animals, or bone fusion data, may not be as precise, but it can be incredibly powerful to combine many different lines of seasonality evidence to gain a more complete picture of site use patterns, both within single sites and across the landscape. Also, combining this evidence with more traditional archaeomalacological methods can help to define whether past harvesting practices were sustainable, therefore providing critical long-term baselines for sustainable resource management. So harking back to the previous example, we've reconstructed the seasonal foraging patterns from different archaeological layers at Xara-Kil. And what we found was that during the early Upper Paleolithic or Apmarian, shellfish are shown to be foraged throughout the year, but with an overwhelming predominance in winter. And this is when shellfish began to appear in this record in great numbers, as part of a broadening subsistence strategy that we see in many Upper Paleolithic sites in this region. So other food resources that begin to appear in this sequence at this time include small mammals and seeds, which are also indicative of broadening subsistence. The winter shellfish foraging pattern that we see is typical of many regions of the Mediterranean. So from the Paleolithic to the Neolithic, this is the most common foraging pattern that we see. In contrast, during the Upper Paleolithic occupation, a little later, when we have cooler, higher seasonality conditions associated with Heinrich Event 4, the shellfish foraging strategy shifts a bit. Shellfish are being collected throughout the year and every season. This Upper Paleolithic or Aurignacian occupation is thought to reflect a back migration of modern humans from Europe into the Levant. So it's tempting to wonder whether the deteriorating environmental conditions associated with Heinrich Event 4 may have created some kind of demographic pressures that instigated the Aurignacian back migration into the Levant. And so foraging of shellfish in every season has in many studies been linked to resource and population pressure. And this may be what we're seeing here, part of a suite of evidence suggesting population and resource pressure close to the timing of Neanderthal extinction. This could be interpreted as evidence of modern humans adapting to environmental and demographic pressures. And just finally, I want to take you through one example from Australia. So this research was led by Dr. Sam Aird as part of her PhD, which I co-supervised, and her primary supervisor was Kat Jarbo, who will be giving their next keynote, which I'm looking forward to. So Sam's done some really interesting work in the Southern Great Barrier Reef, both calibrating different species as environmental proxies and reconstructing seasonal shellfishing practices in Wopabara country in the North Keppel Island group over the last 5,000 years. She found that one species in particular, the moon turban shell, Lunella cinerea, can be used to reconstruct high-resolution climate and seasonal foraging records in this region. Sam was able to link Western science techniques such as sclerochronology and biometrics with traditional ecological knowledge, in particular using both oral histories and the Wopabara seasonal calendar. The calendar is seen here as a pictorial representation of 7 different overlapping phases, and these are based on meteorological and resource availability patterns, as well as spiritual and cosmological understandings. So sclerochronological and archaeomalacological reconstruction suggested that the long-term patterns of Wopabara shellfish harvesting were sustainable, and the seasonal foraging data showed consistent harvesting during the austral spring. This roughly corresponds to the Wopabara season of Konami, which is September and October. The name Konami is extremely significant in Wopabara culture. Konami is the Wopabara name for North Keppel Island, and it's also an ancestral figure. The season of Konami is an important time for ceremony, and in the Wopabara calendar, the clan group totem, Mugga Mugga, or the humpback whale, appears within Konami. So therefore, it seems no accident that shellfish foraging was focused around this very important season. And this study highlights the potential of integrating Indigenous traditional ecological knowledge and Western scientific techniques to provide longer-term baselines for the sustainable management of resources. Such data can potentially enable management practices that foreground Indigenous perspectives. So in summary, zooarchaeological sclerochronology can generate high-resolution quantitative climate records useful for testing and refining climate models. These climate records can be used to understand past human-environment interactions, which may inform our strategies for dealing with future climate change. Combining sclerochronology-based seasonal foraging reconstructions with more traditional archaeological methods and with traditional ecological knowledges can be used to examine sustainable harvesting practices, providing longer-term baselines and foregrounding Indigenous perspectives in ecosystem management. And then finally, I've got some questions for you. So I look forward to hearing your perspectives on these issues as we dip in and out of the different chat rooms. Cool, thank you.
That was absolutely fantastic. I have